So we are starting today with the adder and subtractor as a combinational logic circuit. So what is combinational logic circuit? That is the first question which comes to our mind. So the circuit is going to take some input and it is going to generate the output based on the behavior that we have designed in the circuit. And that's why in the combinational circuit, we are going to find out the present combination which we are going to provide to that circuit. Based on that present input combination of the circuit, we are going to generate some specific output. Because when we have gone through the Boolean functions, we have described there that while writing the Boolean function, how many number of inputs are there, based on that, the input combination is going to change. Let's say suppose I'm having 3 inputs for that circuit, then the Boolean function will have possibly 2 raised to 3 number of input combinations provided for that circuit. And based on that, again, the 8 different outputs we are going to get. But these outputs will be defined by whatever the combination of logic inputs we are having provided for that at the present instant. So we are saying that combinational circuit is combining 2 or more logic gates which are going to form the required function. So let's say that function may be implementation of sum of product. So sum of product means what? We are getting first the products to be done, which is applied for either 2 or 3 variables, and such like this different product terms will be present, and those product terms we are going to add at the end to get the final output. So here the logic gates which I am using will be AND and OR gates. So here AND OR, but it may be possible that the input for those logic gates will be either in original form or it may be in complemented form. And if my input is in complement form, I have to go for application of NOT gate. And that's why here we will find out that the combination of OR and NOT gate will be present. So combinational logic is combining 2 or more logic gates. And these logic gates will be combined to form some particular function. And that function will define the output based on what is the current input for that particular circuit. But now, this is the definition of combinational logic circuit. But combinational logic circuits are broadly classified under these 3 categories. One category is the arithmetic and logic function performing combinational circuits. Another category is data transmission based logic circuit. And third one is code converter based logic circuits. So in this your chapter of combinational circuits, all these 3 types of combination circuit we have to see. Under the arithmetic and logical functions, we have to go for adder, subtractors, then the various gates which are used for that Boolean functions to be defined, and we have to get the minimization of those Boolean functions to be done with the help of K-map, and finally the modified logic diagram for the given functionality circuit we have to define. Either I take the block from this arithmetic and logic function performing unit, data transmission unit, or code converters, we have to follow this same process for that. That means we have to go for the same process of defining first the Boolean function, writing their simplified form with the help of K-map implementation, and then the minimized diagram for that block has to be implemented. Is it clear what is the aim of this chapter, friends? So I will go for first, what is the design procedure for any combinational circuit? So the first step is, in verbal form, your problem will be stated. From that problem statement, we have to define how many number of inputs will be needed and how many number of outputs are going to be generated from that circuit. Now, after defining that many number of inputs and outputs, as a next step, we have to assign the letter symbols for those input and output variables. Once the letter symbols we have assigned, next step is the truth table formation for defining the output corresponding to each of the input combination, and that we have to define with the relationship usage which will be defined in the given problem statement. Then, based on this, the simplified Boolean function for each of the output that we have to obtain. And for doing the simplification of that Boolean function, either we can use K-map, we can use tabulation method, or Boolean algebra rules, which we have completed in all our previous lectures. Once the simplified Boolean function is obtained, the logic diagram we have to draw. Now, when the logic diagram will be drawn, a practical design method will be facing some constraints, and that constraints are based on how many number of gates we are using. For each and individual gate, how many number of inputs are there, and in between the gates, how many number of interconnections we have to provide, and based on that, how much time is needed for taking one output signal from the previous gate to the another input signal of the next gate. And ultimate aim for these all design procedure is minimizing these all parameters which I have mentioned in the practical design constraints. So when the combination circuits are to be designed, we have to get the minimization to be done for applying the number of gates, the number of inputs to every gate, then the number of interconnections for implementing that combinational circuit. And if we are minimizing these all things, obviously the propagation time for the signal flow or signal through in the circuit is going to get minimized. So through this design procedure, we have to have the aim of minimizing all these parameters in real situation. The next thing what we have to cover is the types of adders. So as the name indicates, they are adding the values. But as we are dealing with the digital circuits, they are working on digital inputs. And digital input will either take value as a 0 or 1. So I can define this half adder as it is a combinational logic circuit with 2 inputs and 2 outputs. So here in the definition, we have defined now that it is a combinational logic circuit which is having 2 inputs and 2 outputs. So let's go for this diagram where the block diagrammatic form of the half adder we have defined. And for this half adder combinational logic circuit, the inputs we have defined with the letter A and B, and outputs we have defined with the letter S and C, where this S stands for sum and C stands for carry. Because in the process of addition, the resultant will be the addition resultant and the carry that has got generated by addition of two values. So the aim of half adder is addition of two single bit binary numbers. So we are considering here the two numbers which are consisting of single bit each. Either that value will be 0. So first number we are considering as A and second number we are considering as B. So either its value will be 0 or its value will be 1 as presented in the table. So two inputs, so totally 4 input combinations can be presented for this half adder. Those we have represented in the truth table part of this circuit, where we have written this A and B, because there are two inputs which are specified for this half adder. Now, with respect to this input definition, the sum and carry part we have to mention into this truth table. So when 0 bit is added with 0, that means it is ORing operation, and ORing of 0 with 0 will result in some value of 0 with the carry value of 0. Similarly, if I take the input combination of 0, 1 for A and B, it will result into the sum value of 1 and carry value of 0. But if the input combination of AB is 1 and 0, then sum value will be 1 and carry value will be 0. But if both the inputs are 1, then sum value will be 0 and carry generated will be 1. So from this truth table, we can see that for two defined input variables, possibly 4 input combinations are existing, and corresponding to this each of the input combination, we have to define these output variables as S and C. And for defining these output variables for this input combinations, we have to use the gates, and that gates will be the addition process for these two inputs, as the name of this block itself is addition. But it is said to be half adder because here, while I am doing the addition process, I am not going to consider the carry for that addition process. I am taking only the input combination in addition process. I'm not considering the carry generated or the another third input as a carry for this process. So this block is named as half adder. Right? I have to write this sum output as a representation of some gate. Now for this S column, if you observe the output, in the S column, I am observing that when both the inputs are same, the output generated is 0. And when one of the input is 1, output generated for this sum column is 1. So it is similar to the truth table of the XOR gate. And that's why now to define this output variable of sum from the two input variables of AB, the XORing operation we have to perform. And that we have defined from this truth table column of S. So to represent this S, we have written the Boolean function of XOR gate as A bar B or with AB bar. And we have drawn here the XOR gate symbol, which is connected at the input side with AB variable, and from that the output which we are obtaining is mentioned as sum. While for defining the gate implementation for this carry, if I am observing when the two inputs are 0 or any one of the input for that is 0, the generated carry value is 0. But when both the inputs are 1, the generated carry is 1. So this is exhibiting the behavior of AND gate. So to implement this C output variable from A and B input variables, the AND gate implementation will be done. And that AND gate has been presented over here. So this is a way how from the given problem statement we can implement the logic circuit diagram for the given combinational circuit. So first step what we have done is from the given verbal specification of the problem statement, we have first defined how many number of inputs and outputs that will be needed. Once that has been defined, for the input and output, the later assignment we have done, that is A, B for input and SC for output. If that step is completed, next step will be writing the truth table corresponding to output definitions for each of the input combination. And that will be defined by using this like truth table structure. So to write the truth table, simply first all the combinations of the inputs we have to note down. After that, for addition, we are using these two input bit. According to that, what will be sum and what will be the carry that you have to note down in the output columns related to those possible input combinations separately. From the truth table, we have to extract the logical diagram implementation. And for that logical diagram implementation, which gates are needed, that we have to see from the representation of output variables in form of the input combination presented to it. That we have done separately for individual output variable of sum and then for carry. This is how the output diagram is obtained for this half adder. So the next block is named as full adder circuit. Now the name indicates what? Full. So full means the carry also will be considered at the time of addition. And that's why in this block diagram representation, if you are observing the change, instead of having two inputs, we will have now one another input which is added is Cin as compared to this half adder block. For this half adder block, only two inputs were present, that is the numbers which are to be added. Here the carry is not existing at the input side. But in the full adder, along with these two numbers, the input carry is also existing. And that's why it is named as full adder. It means that at a time, this block is going to accept 3 bits input. And if I am having 3 bits as an input, the possible input combinations I have to represent into the truth table, which will start from 0, 0, 0 up to this 1, 1, 1. I think you are understanding what I am telling to write down this combination for the inputs which will be present. By using the addition for each of that input combination, we will define the two output variables, that is sum and carry out, because this is a process of addition. So as an addition resultant, we are going to get the sum variable and output carry. Now, if the input combination is 0, 0, 0, the sum resultant will be 0 and the carry output will be also 0. If combination for the input is 0, 0, 1, sum will be obviously 1 and carry generated will be 0. In the case of 0, 1, 0 input combination, sum generated will be 1 and carry will be 0. But now, if in the input combination, two ones are present, then sum generated will be 0 and carry will be 1. So wherever we are having more than or equal to two number of ones in the input combination, there some value generated is 1 and also the carry generated is 1. You can have a look for that. If I am having two number of ones, then definitely sum is 0 but carry will be 1. But if the number of ones are odd in number, then sum and carry both will be 1. What we are seeing is, for each of the output variable, we have to get the gate implementation to be done. In previous case of half adder, as we were having only 4 number of output combinations, that's why it was very easy to know that which gate is present or gate behavior is present for implementation of that output variable. But here in this case, 8 number of possible output combinations are present, and because of that, now we have to look for writing the k-map for the 3 variables. Or what I can do simply is, I will look for that column, and in that column, whichever output variables are 1, corresponding to those output variables, the input combinations I will join with the ANDing gates, because this will be represented as sum of products. So here, once we are saying this 1 is represented for A dash, B dash and C. So let's check the first gate combination, as it is a product value. So here ANDing gate has to be represented. This one output is present for the combination of A dash, B dash and C. So we are writing this first AND gate as the input combinations of A dash, B dash, C. Now the next one output for sum occurs for A dash, B and C in dash. So here for the next AND gate, the output which is specified is A dash, B, C in dash. In truth table, the one occurrence for the sum is happening for next combination of 1, 0, 0. That means it is A, B dash, C in dash. So for the next AND gate, the input specified is A, B dash, C in dash. Next one is occurring for the sum for the combination of 1, 1, 1 input. That means all 3 variables are in original form. So we are writing that inputs for AND gate as A, B, C in value. Once this will be obtained, those all product outputs we have to get sum with. And that's why here the OR gate will be represented. So this whole gate implementation will give me the sum output formation. In the same way, for the carry out, from the truth table, we have to look for the one output representation combinations of input. And corresponding to that, the product terms first we have to form, and all the product outputs has to be summed up finally to give the Cout representation in combinational circuit form. So let's check for that. Cout value is 1 for the combination of 0, 1, 1. So it is A dash, B and C in value. But here if you are observing, this we have drawn only for the 2 variables. That means the alternative way what we can follow for the representation is From these variables, we can write down the K-map. For the K-map, we will have 3 input variables. So 3 variable K-map I have to specify. So how that 3 variable K-map will be written for this? That I will show you here. So here, for the 3 variable K-map, how we are writing? Let's say I am having A, B, C in as the variable combination. So I will take the C in over here. So the combinations, how I have to specify? First will be 0, 0 for the column specification, then 0, 1. Then to follow the rule of only one variable change, here after 0, 1, I have to specify 1, 1. Then here it should be needed as the specification at ending position as 1, 0. While for Cin, it will be 0 and then it is 1. So let's say this is now your empty K-map which is ready. Now what we will do is, after having this K-map formation, we have to go for the individual output column. Let's say that column is of sum. And in the sum column, I am finding the output 1. Where I am finding the output 1 for the sum? When I am having this combination as Cin of 0 and the AB value as 0, 1. That means one of the inputs should be 1. So at this condition, I am finding the output for sum as 1. Then here, for this particular combination of A and B as 1, 1 and Cin as 0, again I am finding the sum output as 1 and carry also will be 1. But I am looking for now the block formation or the gate implementation for sum. And when AB is 1, 1, the sum generated will be 1. For AB as a 1, 1, please stop plotting on this. So here I am finding now the next input combination AB as 1, 1 and 1, 0 and the input as 0. So for this condition of input also, the sum generated will be 1. Then the next combination what I am looking for is AB as 0, 0 and Cin as 1. For this, the sum generated will be 1. Again, I will look for the next combination of AB as 0, 1 and this Cin as 1. So for that combination also, sum generated is 1. Here, the next combination is 1, 1 for this AB and C is also 1. So sum output will be 1. In this situation of AB input as 1, 0 and Cin as a 1, the output generated will be 1. So in all these 7 conditions, we will find the sum generated will be at, we have to get the grouping of ones to be done. And maximum possible number of ones we have to group in a single group. But that number of ones should be what? Power of 2 value. That means either it is 2, 4 or 8 in number. Am I right? Yes, I cannot get any of the group to be formed. Am I right? Am I right? So ultimately, the answer what I am going to get is this variable which is of 3 literals, and that variable will be A complement B and Cin complement. So like this, we can have the different variables terms we are going to get from this. So first term I have written here A dash B Cin dash. For this term it will be Cin dash B dash. Please stop doing this. Then next combination will be A dash B dash Cin, and last one term will be the value of ABCin. And by using this in the table, I will again go for the presentation. Here I will stop this presentation for whiteboard and I will go for this. But let's remember these terms, what I have shown you on the whiteboard. Those are A dash, B, C in dash, then this A, B dash, C in dash. Next term is this, which I have marked here, and the next two terms will be like this, which has been mentioned over here. Now I will go for the next representation. So likewise, as I have shown on the whiteboard, you can get the K-map to be used for getting the simplification to be done for these output variables, and from that these circuits you can get implemented. So we have done that for the sum. So these four variables we have obtained already. We have done that from this one output representation in the truth table itself. In the same way, for the C out also you can do, and you can get the Boolean algebra to be used for the simplification either instead of the K-map also. So this is what the implementation for the full adder. Next we will go for the half subtractor. So here again the term is half, that means the borrow consideration for the subtraction we are not going to do. Only the two elements or two numbers of 1 bit each we are going to consider for subtraction. For this half subtractor, again two inputs will be present and two outputs will be present. One is said to be difference represented by DEMadder, and output is borrow, which is borrow output, that will be represented by B0. So corresponding to this input combination, we will have as two inputs, so four input combinations again specified in the truth table. Corresponding to each of the combination, difference and borrow value we have to write. So 0, 0 input combination, difference is 0 with borrow generated as 0. The difference value for the input combination of 0, 1 when I am calculating, the difference to be taken as A minus B. And because of that, in this situation when A is 0 and B is 1, difference value is 1 with the generated borrow as 1. But if the A is 1 and B is 0, difference will be 1 with borrow value as 0. When both the bits values are 1, it will be the behavior for the D as a 0 value, and borrow value will be generated also as 0. Now let's look for this difference column. The difference column, if I am observing, this output behavior is similar to the XOR gate, and that's why here for representing this difference operation, the XOR implementation I have to do. For that again A and B will be specified inputs, and this difference we are representing as D is equal to A minus B. We have not done here the operation of B minus A. Please remember this, friends. If I am writing this as a B minus A for the difference, then the truth table output parameters are again going to change. For this truth table specification, we have taken the difference as A minus B. So you have to remember which process you are going to do, and according to that only in the truth table the D and B0 columns you have to specify. Now we will go for the next output variable, which is B0. So this B0 we are finding, which is simply 1 for the combination of 0, 1. And this we are going to find out when the AND gate A input is going to be complemented. This is a logical understanding that I am telling, but instead of this logical understanding, you can write a two variable K-map. Once for this D and once for this B0, as I have specified for the full addition operation. So after writing the two variable K-map, for this corresponding to D values I have to represent into the K-map. Grouping of ones I have to done if possible into that specified K-map, and the simplified form we have to get. So if I will write the K-map for this, I will find out that we will get here the answer as A dash B plus AB dash. So it is XOR gate specification. While for the B0 to be defined, we will get the term as the value which is this as a bar, and this value is B. So borrow will be defined as A bar B, which we can see from this one value indication, also from the truth table. So 1 is present for the input combination of this as A bar and this as B. So we have taken this ANDing operation for the terms of A bar and B, which is the specification for this B out or borrow out value. In these operations of subtraction, the term which is going to get subtracted is said to be the subtrahend, and the term from which the element is going to subtracted, that is said to be minuend. So these are the verbal parameter specifications for the subtrahend, minuend, borrow, and the related truth table specification and gate implementation for the combinational logic circuit of this half subtractor. So one another combinational logic circuit we will see, and then we will stop today for this lecture. So that logic circuit is of full subtractor. So as name indicates, it is full subtractor. So in subtraction process, the extra term which is there is the borrow in, which is represented over here in the truth table. So here, instead of this x, y, z, you can get the representation to be done as per the truth table that I will give you here with the marking. So this variable you can consider as A, this as B, and this variable as B in. So corresponding to these three inputs, 8 possible combinations that we have noted in this truth table, and for each of the input combination, difference and borrow out we are going to check. But when we are checking this difference, the operation of subtraction we are doing with the order of A minus B. The resultant of that A minus B is obtained, and from that resultant B in is subtracted. So 0 minus 0 is 0, and 0 resultant minus this 0 will be the difference of 0, and the output will be 0 for borrow value. Next is 0 minus 0, which is resultant of 0. But this resultant 0 and this 1 is subtracted from 0 resultant. So difference will be of 1, while the output borrow will be of 1 again. Next, 0. From this 0, 1 has to be subtracted. So resultant will be 1 difference with 1 borrow. And from that one difference, the 0 has to be subtracted, but one borrow will be carried out as it is. So in borrow out, 1 will be present while difference will be 1. The next is 0 is present for A and 1 is present for B. So 1 is subtracted from 0. So resultant is difference 1 with borrow 1. So borrow we will carry forward as it is to 1, but difference 1, from that difference 1, the input borrow of 1 we have to subtract. So resultant is 0. Next, 0 value is subtracted from 1. Result is difference as 1, borrow as 0. So borrow out we will write as 0. But from that difference of 1, again the next 0 value of borrow in we have to subtract. So result is 1. Here in this combination, 0 is subtracted from 1. Result is difference of 1 with borrow 0. Only borrow we will carry forward for this borrow out. But from the difference of 1 from these two bits, the another value of B in of 1 is to be subtracted. So the result is 0. In this way, for next two combinations also, the difference and borrow out will get generated. Now, from this truth table, separately for this D, we have to implement the three variable K map of AB and BN. Take AB in the column specifications and BN in the row specification. And if you are writing the truth table K map accordingly and specifying the ones corresponding to the mean term representation in the K map solution will give the implementation of the gates as like this for the D variable obtained. And similarly for the B out also, with these three input variable combinations, but the output to be taken from this column, the other K map we have to specify. And in the K map, wherever one outputs are specified for B out in the column, corresponding input combinations representation in the K map we have to give as 1 or mark as 1. And the simplification of grouping of ones has to be done, and then we will get the get connectivity like this for getting the borrow output value to be generated for this full subtractor. So as in your homework, try for the K-map implementation for this truth table for the full subtractor and check out whether you are getting this diagram as a logical diagram implementation or not. Today here I will stop and I will float now your attendance